Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics, lecture number 5. Let's see in lecture number 4 what we have studied. In lecture number 4, we continued with the method of successive approximations. We did a few examples as well, and after that we went on to study the Adamian decomposition method and the direct computation method. These all were the methods to solve integral equations. One by one हमने इन methods को देखा. Lecture number 3 में भी method of successive approximation से हमने solve किया कुछ resolvent kernel की मदद से. फिर हमने directly हमने ये method of successive approximation use किया U1, U2, U3 निकाल के. उसके बाद Adamian decomposition method था जो कि एक series solution की form में integral equations का solution होता है को हमने देखा. आफ्टर दैट डायरेक्ट कंप्यूटेशन मेथड जिसमें हमने स्पेशल किस्म के कर्नल्स के लिए यानी सेपरेबल कर्नल्स के लिए हमने ये मेथड पढ़ा था which was applicable to Fredholm integral equations only. Alright, so these were the 3 methods which we studied in last lecture. In today's lecture we will study non-homogeneous integral equations of second kind with degenerate kernels. If you remember our first lecture, we had studied special kinds of kernels, and this degenerate kernel was one of them. Alright, so we will study non-homogeneous integral equations of second kind with degenerate kernels. We will see examples for that as well, and then homogeneous Fredholm integral equations with degenerate kernels. Alright, homogeneous Fredholm integral equations with degenerate kernels and few examples for that as well. So these will be our 2 main topics for today's lecture. I hope you will enjoy this. So first of all, non-homogeneous integral equations of second kind with degenerate kernels. The kernel kx eta in Fredholm integral equation is degenerate if it is the sum of a finite number of products of functions of x alone and functions of eta alone. It is of the form kx eta. If you recall, the separable kernels have 2 product functions, one of x, one of eta. But here we have sum of such functions. We can still call it separable kernel as well, but degenerate is a more appropriate name for these type of kernels. So what we do is we try to write our kernel as a sum of product of 2 functions, with one entirely of x, one entirely of eta. So any kernel which can be written as this, one function is of x, one of eta, and you can write the sum of such product functions, right? Then we call this kernel a degenerate kernel. Consider a separable kernel in the form, so if it is a separable or degenerate, then we can write it like this. There is no problem because this is the definition of separable or degenerate kernel. So we are assuming that ak x and bk eta, they are continuous function in a square. Like x goes from a to b and eta goes from a to b. In this intervals they are continuous and linearly independent as well. If they are not linearly independent, then there is no charm in writing as a sum of these functions, because if they are depending upon each other, then you may one term is depending on the other term. Alright, so it doesn't look good. So basically if they are linearly independent, their linear combination will be a good choice. Substituting the value of kernel in the Fredholm integral equation. This is the Fredholm integral equation which we wrote in the previous slide. Let me show you this again. Kx eta. And now as we said, this kx eta is a degenerate kernel, so I can replace this kx eta by this one and I get this. You see, kxt is replaced by sum of ak and bk. Alright, and now because a, k, x are not depending on eta and integration is with respect to eta, so what we can do is we can bring all a, k, x out of the integration. This is the same as we did in the last lecture. At the end, in direct computation method, we said if kernel is separable, I can bring the x term outside of the integral. So we are doing the same thing. So summation k goes from 1 to infinity, a, k, x, they are outside, and integral is only on b, k, eta, u, eta, d, eta. Alright, so now again what we said, this is a constant, so we can call it alpha. But now the problem is it's not one integral. these are many integrals for every bk, like b1, b2, b3. For every bk, I get a different constant. So just call them ck, because they are constants, unknown constant, but they have to be constants, so we can define them as ck. So let's define ck to be a to b, integral of a to b, bk eta u eta d eta. So these are not just one constant, these are infinite many constant, k1, k2, c1, c2, c3, c4, so on. These are all constants. So if I replace this ck in this colored equation, so we can write this as ck. So all I got is fx plus lambda ck ak, right? And some k from 1 to infinity. So what you got is ux is equal to fx plus lambda, some k goes from 1 to infinity, and ck ak, because this whole thing becomes ck, so you got ck ak. There is no bmx here. This is there should not be bmx here. This is a typing mistake here. All right, we will multiply this whole equation by bmx. All right, bm is the same, this b eta, this bmx, this one. So if you multiply it by bmx, now this bmx should be here. It's a typing mistake again. This bmx should be here, bmx. All right, this is only f of x, this is bmx. In the lecture notes, I will correct this. All right, in the lecture notes, you will see this bmx written down here. All right, so pardon my mistake here for these slides. Now if we multiply by bmx and integrate, if I integrate, you see you have bmx ux on the left hand side, fx bmx, see? So it means this bmx should be here, not here. It should be here. Plus lambda a to b ck bmx akx dx. So I multiplied everything by bmx and integrated it. After integration, again you see here, summation, the ck is constant, so I can bring this outside the integral, but you cannot just bring ck out, because you have to bring this summation out as well, because ck has to be inside the sum. All right, so now this is again a constant. If you see, this is a constant, because everything is being integrated over the constant limits, it has to be a constant. Similarly, this fx and bmx dx, this has to be constant as well. All right, so we define them by fm. You see, fx times bm is fm, and here this is bmk, so I can write amk. You see, m and k, there are two subscripts, mk, so I'm writing them amk. Here is just one subscript, m, so I'm writing a f sub m. So if we define these constant to be these two integrals, then this whole thing will become, this is already cm, we have already defined this to be cm. You see, this is exactly the same. This is cm, this is fm, and this is amk. All right, so with this setting, the previous equation reduces to cm equal to fm plus lambda summation ck amk. Here you see. All right, cm is equal to fm plus lambda summation amk ck. M goes from 1 to n. Right, m goes from 1 to n. This is a system of n linear equations. You see, these are all constants inside. So this is a system of n linear equations in C1, C2, C3 up to Cn. Here fm and amk are known since we are given bmx, fx, and axk. You see, if you look at the formation, ak and bm, they are given to us. So amk is a known constant. Bm and fx are given to us. Again, these are known constants. So what is unknown? Unknown is only ck. Cm and ck, these are only unknowns. So cm and ck are unknowns, amk and fm are known functions. That's why these are the equations in ck, in c1, c2, c3. These are not in fm or amk. They are known constants. The colored equation in the matrix form, if I write this in matrix form, what you will get? See, c1, c2, c3 up to cn, f1, f2, f3 up to fm. All right, and right inside is like that. So this is your C equation. We can call this vector C, we can call this a vector F, we can call this matrix A, and we can call, this is being multiplied by C again. So there is a lambda and a vector C as well. So let me simplify it. Alright, so this is our equation and we need to convert this to matrix form. So it's basically for m goes from 1 to up to n, what we have. So for each m I can write one equation. So when m is 1, this is c1 is equal to f1 plus lambda k goes from 1 to n a 1k ck, right? So you can write it as f1 plus lambda a11 c1 plus a12 c2, because k goes from 1 to n. So k1, k2 up to kn. So 1n cn. So this is what you got for c1. Similarly, for c2, you will get f2 plus lambda a21 c1 a22 c2 plus a2n cn. So on, for m is equal to n, you will get cn is equal to fn plus lambda an1 c1 plus an2 c2 plus so on up to an n cn. These details were missing in the slide, of course. These things are very straightforward, but I thought I should just write it for you guys. So this is a set of n algebraic equations. So it's a system of equations, right? So what you can do is you can make this left hand side the whole vector. f1 up to fn is vector. Here a11, 1 to 1n are being multiplied by c1, c2 up to cn. I have already called c1, c2 up to cn as one vector, capital C. Alright, so it means the left hand side can be written as c1, c2 up to cn. This is one vector, is equal to f1, f2 up to fn plus lambda and a is being multiplied. So a11, a12 up to a1n are being multiplied by c1, c2 up to cn. Alright, so this is your first equation, a11 c1, a12 c2 up to a1 n cn. Similarly, a21 c1, 22 c2 and 2n cn. So on, an1 c1, n2 c2 and ann cn. So this is your matrix. This is what you got in that slide. So we wrote directly after this one, we wrote directly this system, right? So the missing details are in here now. They are of course very easy. At this level you should be able to do this on your own. But anyway, if I call this vector as capital C, if I call this vector as capital A, if I call this matrix as capital A, then what I can write is, this is C is equal to F plus lambda AC, right? F plus. Now this C and C, you can combine them. C minus lambda AC is equal to capital F, right? And now if you take this common, if you take C common, then this will be C I minus lambda A C is equal to F. This is what you got. So this is what you got over here, you see. I minus lambda A C is equal to F. So here one lambda is missing, typing mistake, and a vector C will come here as well. Alright, so it is F plus lambda A and C. So from here, this is a system of algebraic equation in matrix form. Alright, so thus with the help of this method, we can say that solving an integral equation is equivalent to solving linear algebraic system. Either solve the integral equations or solve the algebraic equation. So which one is easier? Of course algebraic equation is easier. Solving algebraic equation, no derivative, no integral sign there, just constants everywhere, one unknown vector, right? So there are many methods to do that. You can take the inverse, multiply on the right hand side, you will get C or something like that. So also we know that the theory of linear system of equations, that the equation has a unique solution. This equation has unique solution if this is non-singular, right? The determinant of I minus lambda A is not 0. If this is if this determinant is 0, then you may not have unique solution. Either the solution will not exist, or there will be more than one solution. There will be infinite many solutions. For one unique solution, this matrix on the left hand side, which is being multiplied by C, this should be non-singular. If it is non-singular, you can take the inverse, multiply inverse on the right hand side, you will get just one solution. Alright, so if this is not the case, if it is a singular matrix like the determinant is 0, then there will be either no solutions or infinite many solutions. Alright, so either infinite or no solution when the determinant is equal to 0. This is straightforward from linear algebra. I guess nothing is difficult for you guys at this level. You have studied linear algebra at many places, and this is a very basic theory of system of linear algebraic equations. So solving the integral equation has been converted to solving the system of algebraic equations. So let's see an example of a Fredholm integral equation. Let's see, we have this example: ux is equal to x plus lambda 0 to 1 1 plus x eta u eta d eta. First of all, you have to check whether this is a degenerate kernel or not, whether this can be written as a sum of the product of two functions, which is 1 of x and 1 of eta. It's very clear. The first one is 1 is a function of anything, right? And x eta, 1 is a function of x, 1 is eta. So this is a degenerate kernel. All right, this is a degenerate kernel, so we can basically solve it by that method, by converting it to a set of algebraic equations. All right, so let's see. So example, ux so this is your example: ux equal to x plus lambda 0 to 1 1 plus x xi u xi. You can write eta if you want. I wrote xi. We are using t, xi, eta, anything. This is a dummy variable, so it's your choice, whatever you want to write. So here your kernel is degenerate. Here your kernel kx xi is 1 plus x xi. This is clearly a degenerate kernel, right? So you can write this as f1 g1 plus f2 g2, right? And f1, where f1 of x is 1 and g1 of xi is also 1. Similarly, f2 of x is x and g2 of xi is also xi. So see, this is f1 g1 plus f2 g2 is your kernel. It's very easy to see that here, right? Yeah. Now if you rewrite this one from 1, if you rewrite this one, you can write this as ux is equal to x plus lambda 0 to 1 mu xi dxi, because it's 1 times this one, plus lambda x can come out of the integral, and you have xi u xi, right? U xi, u xi, xi u xi dxi. So you can write it like that. I multiplied u xi with 1, and then x xi u xi. X is independent of xi, so you can bring it outside, so you got this one. All right. So now if you call this as, if you multiply, because we multiply with each bmx, right? So our bm's are 1 and x, right? If you want to write bmx, if you want to write the same notation, bm and what we wrote over there, bm and a k, right? bm and a k. So in that notation, it will become b1 a1, b2 a2. All right. First of all, we have to call this. We have to call this C1, right? And we have to call this C2. Right, this was our notation that when in degenerate kernels, because this is a constant, this is another constant, so they can be called C1, C2. Right? So your equation becomes Ux is equal to x plus lambda C1 plus lambda x C2. Right? See, x plus lambda C1 plus lambda x C2. Right, this is what you got. Now if you multiply this 1 by 1 and integrate, if you multiply by 1 and integrate, you will get integral from 0 to 1 ux dx is equal to integral from 0 to 1 x dx plus lambda C1 is constant, so integral is just from 0 to x, plus lambda C2 is constant and integral is from x dx. Alright, so this is again C1. If you look at here, just integral of ux dx is C1. This is C1, and this is x squared by 2 from 0 to 1 is 1 by 2, plus lambda C1, this is x from 0 to 1, lambda C2, this is x squared by 2 from 0 to 1. So you got 1 by 2 plus lambda C1 1 plus lambda C2 1 by 2, and this is C1. So now the equation you got is C1 times 1 minus lambda minus C2 times lambda by 2 is equal to 1 by 2. Right? See, C1 and C1, if you take common, it's 1 minus lambda, and then you have lambda C2 times lambda by 2, and 1 by 2 is on the right hand side. So this is one equation. Now what I will do here, I will multiply by the other BMX. Other BM is x. You see, one is 1 and second is x. This is 1 and this is x. So I will multiply by x now and integrate. Right? This equation. This, let's call it 2. So now I multiply 2 by, now multiply 2 by x, because this is our second function of x in degenerate kernel. We obtain x ux dx from 0 to 1 is equal to x square from 0 to 1 dx. You see here, this is x ux, this is x square, and lambda c1x and lambda c2x square. So plus lambda c1 x dx and lambda c2 x square dx. Alright, 0 to 1, 0 to 1. So multiply by x and then integrate. And this is your c2. We call it c2. This is x cubed by 3 from 0 to 1, it's 1 by 3. This is x square by 2, so it's 1 by 2. This is x cubed by 3, so it's 1 by 3. Now you see, this is c2 and this is c2. So it's c2 times 1 minus lambda by 3. See, this is lambda by 3. And plus, this is c1, so it's minus lambda c1 is equal to 1 by 3. So this is your second equation. So you got a system of equation here. Right? So your system is basically becomes here c1 times 1 minus lambda and c2 times 1 minus lambda by 3. c1 is equal to 1 by 3. So you got is the coefficients of c1 is 1 minus lambda and minus lambda. So you got 1 minus lambda and minus lambda. And c2 has minus lambda by 2 and 1 minus lambda by 3. So minus lambda by 2 and 1 minus lambda by 3. So these are the coefficients of c1 and c2, and you have c1, c2 is equal to, in first equation you had 1 by 2, in second equation you had 1 by 3. This is lambda by 2. See, it's lambda by 2, c1, so this is lambda by 2. So now this is correct. So these let's say this is your equation number 3 and this is your equation number 4. So 3 and 4 in matrix form. 3 and 4 in matrix form is this one. Alright. So if you want to write this in that notation, which was I minus lambda a c, right? if you want to write this in this form, then what is your A? A is the I is 1001. It's very clear. The coefficients of lambda, gives you A. So 1 by 2, 1 by 2, 1 by 3. This is your A, right? So your A is basically 1, 1 by 2, 1 by 2, 1 by 3. This is your A, and F is the right hand side, which is 1 by 2, 1 by 3. So in this notation, it is I minus lambda AC equal to F. So this is A and F. And of course, C is C1, C2, and I is 1001. Right? So now clearly, if these are the four vectors, matrices, you can clearly see I minus lambda A is nothing but this whole thing. Alright? So this is what we got so far. So this is the matrix form which we arrived at by converting the integral equations into the set of linear algebraic equations. So if I minus lambda A, which is basically 1 minus lambda minus lambda by 2 minus lambda by 2 and 1 minus lambda by 3. If this is invertible, that is determinant of I minus lambda A is not equal to 0, then the unique solution is C equal to I minus lambda A inverse times F. So this is your, because if it is invertible, you can multiply by the inverse on the right hand side, and this gives you the unique solution of C, right? And if determinant of I minus lambda A is equal to 0, right, then integral equation, then the integral equation has no solution or infinite many solutions. So how we will get to know how many solutions, whether it's infinite many or not. So let's see what are those values. Let's say determinant of that 1 minus lambda. So it was 1 minus lambda by 2 minus lambda by 2 minus lambda by 2 and 1 minus lambda by 3. This was the determinant, right? So if you simplify it, you will get, so let's see if when this is equal to 0. So this implies that if you simplify it, you will get lambda square minus 16 lambda plus 12. So if you simplify this, you will get lambda square minus 16 lambda plus 12 equal to 0. So from here your lambda is so this is what you got. Lambda is this one. So if lambda is not equal to 8 plus minus 2 square root of 13, then C is the inverse of 1 minus lambda by 2 minus lambda by 2 minus lambda by 2 and 1 minus lambda by 3 inverse times F. So this will be your solution. Alright, but if lambda is actually equal to 8 plus 2 square root of 13 plus minus, right, then we just took that determinant of I minus lambda A is actually equal to 0. So there will be no solution. So either no solution or infinite many solution, right? Now see, your determinant with these values, your determinant will become, then your integral I minus lambda A will have this form, 1 minus lambda by 2. So 1 minus lambda by 2 is 1 minus 4 minus 2 square root of 13, 4 minus square root of 13, 1 because you divided by 2, lambda by 2, and minus lambda by 2, so that is minus 4 minus square root of 13, again lambda by 2 minus 4 minus 13, and 1 minus lambda by 3. So 1 minus lambda by 3 is 8 by 3 and minus 2 by 3 square root of 13. So this is what you will have, right? Your coefficient matrix will be this one. So if you simplify it, you got, this is 1 minus lambda. So this is 1 minus lambda, not lambda by 2. So you got 1 minus 8 minus 2 square root of 13. This is lambda by 2. So this is equal to minus 7 minus 2 square root of 13 minus 4 minus square root of 13 minus 4 minus square root of 13 and minus 5 by 3 minus 2 by 3 square root of 13. So this is your constant matrix. So if you take the augmented matrix of the system, augmented matrix will be this coefficient matrix with the right hand side. What is your right hand side? 1 by 2, 1 by 3, right? 1 by 2, 1 by 3. You need to solve it. So 1 by 2, 1 by 3. Minus 7 minus 2 square root of 13 minus 4 minus square root of 13 minus 4 minus square root of 13 and minus 5 by 3 minus 2 by 3 square root of 13. This is your coefficient matrix, and 1 by 2, 1 by 3 is your right hand side. So you need to solve it. If you reduce it to echelon form, you will see that the system is not consistent. Alright, if you divide this by 1, row 1 multiplied by 1 over minus 7 minus 2 square root of 13 will give you, will make it 1 minus 4 minus square root of 13 minus 7 minus 2 square root of 13 and 1 by time minus 7 minus 2 square root of 13. This is what you will get, right? And here you have the same thing. Then you can multiply R1 by this number, because I want to make here 0, right? So you can multiply this 1 by minus 4 minus 13 and subtract it, or plus 4 plus 13 and subtract it from R2. So this will change R2, right? So your new R2 will be 1, this 0 here, and here it will be minus 5 by 3 minus 2 by 3 square root of 13 minus plus you multiplied this by 4 minus square root of 13 and 4 minus plus square root of 13 and divided by minus 7 minus 2 square root of 13, right? Similarly here you will get 1 by 3 minus the same thing. Alright, now for the system to be consistent, this and this either both will be 0, then you will get infinite many solution. If they are not equal, if one is 0 and the other is not, then you will be in trouble. Alright, so from here it can be easily shown that if you simplify this one, alright, and simplify this one, if this is not equal to 0 and this is equal to 0, it means the system is inconsistent. Inconsistent means it has no solution, right? So this is the case in our problem. The system will not have a solution in this case, so you are not getting any solution for that. So this so lambda has to be not equal to this number to get a solution of the system. If lambda is equal to 8 plus 2 square root of 13, then your system will not have any solution, and of course our equation will not have any solution. Alright, so basically in this scenario you are not solving the integral equation as it is, you are converting your integral equation to the system of algebraic equation, and you solve the algebraic equations to get the solutions. Alright, so I did this example, x plus lambda 1 plus x eta u eta. there is one more example. Again, it's a Fredholm equation, and again it's a degenerate kernel. You see, your kernel is sum of two terms, and each term is the product of two functions, one of x and one of eta. Here first function is x and g1 is eta square. Here f2 is x square and g2 is eta. Alright, so again you have two functions. You can follow the same scheme and write the corresponding algebraic system, and you can find the values of lambda for which you get the solution, and for the values of lambda for which you don't get the solutions. Alright. The next is the homogeneous Fredholm integral equation with degenerate kernel. What if the right hand side becomes 0 of that linear system? The system of algebraic equation, if there is no right hand side, then what you will do? Alright, so basically there is no f of x in your equation. You see, there is no f of x in your equation. Again, if you can write your degenerate kernel as akx and bk eta, then your equation will become this one. You can bring this akx out. Same procedure, we are not changing anything. Only fx is missing in your equation. So we call this thing as ck, axk, same formulation, everything is the same. What is the difference? The difference is when you got this set of linear algebraic equation, the right hand side is 0. Alright, the right hand side is 0. So again, if the determinant is not equal to 0, then c is equal to 0, which gives u is equal to 0, a trivial solution. When the determinant is equal to 0, then we have the non-trivial solutions, and ux will be not. So in this situation, we have to have the determinant of this matrix equal to 0. The reason is, if the determinant of this matrix is not equal to 0, then we'll get the trivial solution, and we don't want trivial solution for the homogeneous equation. See, I know if u eta is 0 and ux is 0, it's always the solution. For homogeneous integral equation, ux equal to 0 is always the solution. I am not looking for that. I am looking for non-trivial solutions. So for the non-trivial solution, I have to have the determinant of I minus lambda a to be non-zero. Alright, so let's see an example here. This is an example of the degenerate kernel. You see, let's have an example here. Solve the integral equation ux, which is lambda 0 to pi and so on. This is an example of a degenerate kernel, and we will see how we get the trivial and non-trivial solutions here. So your equation is ux equal to this is your solution. This is your integral equation. All right. So let's say this is an example. So here, this is your kernel. So kxt, I'm writing t now, not xi. So this is your kernel, and clearly this is a degenerate kernel. One is a function of x, one of t. One is of x, one of t. So this is a degenerate kernel or separable kernel. We can write this as akbk. We can write this as summation akx and bkt. Right? One is of x and one is of t. And k goes from just 1 to 2 because there are just two terms, not infinite many terms, right? So a1x is cos square x and b1t is cosine 2t, right? a1 b1, a2 b2. So a2 is cos 3x and b2t is cos cube t. So this equation will become ux is equal to lambda integral from 0 to pi a1 b1 plus a2 b2 u dt, right? So this will become lambda a1, because this is a function of x, so you are left with b1t ut dt plus lambda a to x 0 to pi b to t u t dt, right? So we call this one b1 ut as c1 and b2 ut as c2, right? This is what we write. So what you got is ux is equal to lambda c1 a1x plus c2 a2x, right? This is what you got. So what will be a11, a12, everything here? From here, your system of linear equations is a minus lambda I c equal to 0, right? Because right hand side is 0, there is no f of x here. So where a is a11, a12, a21, a22, and a11 is 0 to pi b1 x a1x dx, a12 is 0 to 1 a2 b1 b1 x a2 x dx, a21 is 0 to pi b2 a1, and then a22 is 0 to 1 pi b2 a2 x dx. And if you replace the values, b1, b2, we know everything. You see b1, b2 is given, a1, a2 is given. If you replace the values, you should get are a11 is 0 to pi, right? b1 a1, b1 x a1 x dx. So if you replace the values, it's cos 2x cos square x dx from 0 to pi, and the answer you should get is pi by 4, right? I'm skipping the details of integration. It's just a simple integration. You can easily solve it. You should get pi by 4. I'm writing the answer. If you do it, I'm writing the answers. If you do it on your own, you should match with them. All right. Similarly, if you solve for a21, you should get 0. a12 is also 0. Right. I'm skipping the details. You can clearly add them up, and this should be pi by 8. So these are the 4 values you got, and now your so therefore your matrix A becomes pi by 4, 0, 0, and pi by 8. All right. So if this is the case, then what will be I minus lambda A? I minus lambda A will be 1 minus lambda pi by 4, 0, 0, and 1 minus lambda pi by 8. Right? So this is what you got here. So now this is your equation. So this is your I minus lambda A, and our system is I minus lambda A is equal to 0, right? Our system is I minus lambda A times C equal to 0. Right? To get non-trivial solution, as said before, if I minus lambda A, if determinant of A is not equal to 0, then it's invertible. Invertible means then your C will be I minus lambda A inverse times 0. So this will give you a 0 solution. So 0 is a trivial solution. We are not looking for trivial solutions. We are looking for non-trivial solutions. All right. So for non-trivial solution, we must have the determinant equal to 0. That is, I minus lambda A determinant has to be equal to 0 for non-trivial solutions. So this will give you the values of lambda, permissible values of lambda. So if I solve it, what is 1 minus lambda pi by 4? 0, 0, 1 minus lambda pi by 8. This thing has to be equal to 0. If this is equal to 0, then your the determinant of a diagonal matrix is just the product of the diagonal entries. So this is easier here. It's a product of the diagonal entries. is equal to 0. So from here lambda is equal to 4 by pi and 8 by pi. Clearly these two are the values. So these are the two values which will give you non-trivial solutions. Alright, so these are called the eigenvalues. Any algebraic system where the parameter, the value of the parameter which gives non-trivial solution is called the eigenvalue of that matrix. Alright, so this is the eigenvalue. So these are the eigenvalues which will give you the non-trivial solutions basically. So there are two eigenvalues, 4 by pi and 8 by pi. These are called the eigenvalues of the integral equation. Eigenvalues of integral equations, the given integral equation. Alright, now eigenvalues give you non-trivial eigenfunctions, and those will give you the solutions of the integral equation. So now if we take one by one, if we take lambda pi by 4, then your system is 1 minus, if lambda is pi by 4, this will become 1 minus 1, 0, 0, and lambda pi by 4 by pi gives you 1 by 2. 1 minus 1 by 2. This is your system. C1, C2 is equal to 0, 0. I just replace the value of lambda here. So this is 0, 0, 0, and 1 by 2 is equal to 0, 0. And this gives you, first equation gives you nothing, second equation gives you C2 is equal to 0. So C2 is 0 and C1 is free. It can take any value, because I didn't get any value of C1, so it's free. That's why we are getting infinite many solutions here. Alright, so solution is ux. What was our solution? If you recall, solution was C1 a1x plus C2 a2x. This was our solution. In this case, C2 becomes 0, C1 is arbitrary, right? So you got lambda C1 a1x. Lambda is 4 by pi, C1 is C1, and a1x is cos square x. This is given, a1, the value of a1. If you look at the beginning, see a1 is cosine square x. So this is the case. Now, so u1x, I can call one function as u1x. You can call it cos square x. Because C1 is arbitrary, you can, for convenience, take C1 is equal to pi by 4 for convenience. Similarly, you have the second eigenvalue, which is 8 by pi. For 8 by pi, your solution will be C1 is equal to 0 and C2 is equal to arbitrary. It will be free variable, right? So in that case, your ux will become lambda C2 a2x, because this time C1 becomes 0. So C2 a2x, so lambda is 8 by pi C2, and what was a2x? If you go back and see, a2x is cosine 3x, so you got cosine 3x. Alright, so again for convenience, you can take C2, because C2 is arbitrary, it can take on any value, so C2 can be taken as pi by 8. So if you take C2 to be pi by 8, you will get 1 as a coefficient, and you can write your second solution u2x as cosine 3x. Alright, so these are your two solutions for the integral equation. Alright, so you can call anyone as a function of the integral equation. So that's how you solve a homogeneous Fredholm equation with the help of eigenvalues and eigenfunctions. These are called eigenfunctions, because for every eigenvalue you get one function that is a solution of your integral equation, that is called the eigenfunction, and these are non-zero solutions of the integral equation. Alright, so this was the example which we just solved with the help of linear systems. We find out the eigenvalues lambda and the corresponding eigenfunctions, which came out because cube x and cosine 2x in our case. Alright, so you can adopt the same procedure to solve any homogeneous Fredholm equation. So this is the last example for today's lecture. Let's review what we have studied so far in lecture number 5. Non-homogeneous integral equations of second kind with degenerate kernels. We did one example, and again homogeneous Fredholm integral equations with degenerate kernel and one example. So In homogeneous Fredholm equation, the linear system which you get is a homogeneous linear system. What do we mean by the homogeneous linear system? The right hand side of the system is 0. And we can easily find eigenvalues and eigenfunctions with the help of linear algebra, that take the determinant of the coefficient matrix to 0, find out the values of lambda. Those are the eigenvalues, and corresponding to that eigenvalues you get the eigenfunctions, which are actually the solutions of integral equations. All right, so a homogeneous one is little easier. All right, but in the non-homogeneous case, you can get a unique solution. So you have to adopt different values of lambda. If lambda, in our example, it was something like, I think, 8 plus minus 2 square root of 13, if I remember it correctly. So if lambda is not equal to that, we are getting the unique solution of the homogeneous equation. If lambda is equal to that value, we didn't get any solution of the integral equation. In homogeneous example, I got 2 values of lambda, and those 2 values of lambda give me 2 solutions. All right, so this was it. This is it for today's lecture. तो इसमें हमने थोड़ी सी डिफरेंट स्कीम अपनाई है इंटीग्रल इक्वेशंस को सॉल्व करने के लिए. आई होप यू अंडरस्टूड इट. डू द एक्सरसाइजेस, डू द प्रैक्टिस एग्जांपल्स एंड ट्राई टू अंडरस्टैंड द कॉन्सेप्ट्स, of course to reinforce the ideas which we have just learned. I hope you understand it well, and I will see you in the next lecture, in lecture number 6. Till then, Allah Hafiz and Assalamu Alaikum.